everyone is doing fine. We're just giving a couple of minutes to make sure everybody had a chance to join. Any questions on assignment 3? Can I talk more about unit testing? What do you want to know in specific? I know we might have finished briefly last class, but you can be a little bit more specific about exactly what you want to know. So remember again, in the unit test, you want to do unit, JUnit tutorial. And you want to look at the documentation here just to understand the annotations. Once you understand these annotations and how to assert, you should be good to go. I'm not sure what exactly you want to know about unit testing. The examples in assignment 3 should be sufficient to kind of give you examples on how to get going from there. If you have a question, like a more specific question about what you want me to expand on, I'd be happy to answer. If not, just ask on Piazza and I'll try to get to the bottom of it. Are any of these even open? I think I erased everything. Yeah. All right, so I'll move forward since you don't have a follow-up question. Just let me know if you have anything more specific and I'd be happy to try to break it down. Okay, so hopefully y'all can see my screen. This lesson is on software lifecycle models. This is still part of the overview of the course, right? So still a little bit in the introductory phase. We discussed in our previous actual lecture, because we have had other lectures, but it's been on tools. In our previous actual lecture, we discussed software engineering, right? Why do we need it? What is it and why do we need it? This is about software lifecycle models. And you remember those 5 generic phases I briefly went over that make up a lifecycle model. We're going to be discussing those in a little bit more depth, not too in depth, just still a brief overview. And then we're going to have future lessons dedicated to each of those phases. We'll discuss some sample software engineering lifecycle models, their main pros and cons. And then we'll wrap up the lesson with a quick list of classic mistakes in software engineering, which are just well-known ineffective development practices that, when followed, tend to lead to bad results. So moving forward, the gentleman you see here is Professor Barry Beam of University of Southern California. He is considered one of the fathers of software engineering. And he was asked basically a couple of questions, but the main question was, what is a software lifecycle, right? So what is a software lifecycle model? And he said a software lifecycle is the sequence of decisions that you make, and is fundamentally those decisions that are going to determine the history of the software that you are going to build. All right, and that other people are going to use. So a process model is basically answering the question of, what do I do next and how long should I do it for? All right, that's the main takeaway you should get from what is a software lifecycle model. So what is a process model? It's basically a prescription for what should I do next? How long should I do it for? And each model will have different ways of doing this. All right. And it's important to understand which models are good for which situations. Criticality of the software also plays an important role when choosing a model, and so does expected variability. So again, criticality meaning if I fail, right? If I introduce a bug, how critical are the consequences of those bugs? For example, are people's lives at stake? Are people's health at stake? Maybe even how much money is at stake, right? So criticality pertaining to the consequences of failing, of introducing bugs, or not understanding the requirements correctly. And the variability, so it says here, the expected variability also influences the model that you choose. And by variability in the requirements, we mean, well, are we allowing for changes in the requirements as we move forward? Or do we expect changes to happen? Is our stakeholder unsure of what exactly it is they want built? Are they going to come back later on and change their mind? You have to take that into account as well. All right, so there's many ways you can make the decision of which model to pick. Small projects are usually appropriate for agile. Larger projects may require a more rigorous approach. You may even use multiple lifecycle models within a single project. Right? If the project is very large, you might break it down into smaller projects that then you can apply agile to. The bottom line is that choosing the right lifecycle model is of fundamental importance. So in order to pick the right lifecycle model, we need to actually see some of them. And as you're exposed to more and more style, different disciplines in them, then you will be able to apply them to the appropriate problem case. You have seen this slide before. It is of the traditional software phases. And we recall software engineering is an important and critical discipline concerned with cost-effective software development. It is based on a systematic approach that uses appropriate tools and techniques, operates under specific development constraints, and most importantly, follows a process, right? The process being one of these models. And they usually consist of these generic traditional phases. Again, they might call them differently. They might name them differently. They may even order them differently or overlap them, cycle through them at different iterations, at different speeds. But they mainly consist of these 5 generic phases. First one is requirements engineering, followed by design, implementation, verification, and validation, and then finally maintenance. Now that first one, requirements engineering, is the field within software engineering that deals with establishing the needs of stakeholders that are to be solved by the software. All right, so again, it's establishing the needs of the stakeholders. So eliciting the requirements, understanding what it is that we need to solve. Why is this phase so important? In general, the cost of correcting an error depends on the number of subsequent decisions that are based on that first decision, right? Therefore, errors made in understanding requirements have the potential for greatest costs because many other design decisions depend on them, and many of the follow-up decisions depend on them. The cost grows dramatically as we go from the requirements phase to the maintenance phase, because if we discover a problem later, to correct the error, we're left to undo a lot of the decisions that we made before. Right, so that's what this little bar graph is showing. Right, the cost of late correction. On the y-axis, I have the cost of error correction. On the x-axis, I have the phases in the order that I usually implement them. And what it's saying is that the cost of correction is cheaper in the beginning than it is towards the later phases. All right? Since these later phases depend on the decision made in earlier phases, if I find an error in the later phases, it usually means there's errors in the earlier phases as well. I kind of have to rewind and find out where's the root of my error and then correct going forward again. So it becomes that much more costly. So this is an extremely important phase that you want to try to get as good as possible. Now, how can we collect the right requirements? Well, through a set of steps. We have elicitation, which is the collection of requirements from stakeholders and other sources, and can be done in a variety of ways. Then we have requirements analysis, which involves the study and deeper understanding of the collective requirements. Specification of the requirements, which is the collective requirements are suitably represented, organized, and saved so they can be shared. So again, you elicit them, right? So that means you gather them. You survey, you ask questions, whatever. We'll go through a lesson that digs into this much deeper and gives you different styles of eliciting. Then we analyze those requirements, which means we study them deeper. We want to make sure we're actually understanding them appropriately. Do we have to re-ask? Do we have to word it differently? What do we have to do to make sure we have to understand? We actually understood it as it was explained. And then we create specification from those requirements after we analyze them. The specification is the way that we communicate the requirements across the board, across all the stakeholders, whether that be diagrams, charts, just plain words, pictures, whatever it is. We need to come up with this so that we can then further communicate appropriately to all the stakeholders. That's the people that actually came up with the requirements, the people that collected the requirements, the management, our developers, our QA team, right? Our testers, etc. Right? This is how we're going to share the specification in order for everything to be validated. So in the validation, you're making sure that they're complete, consistent, not redundant, and so on, and that they satisfy a set of important properties for the requirements. And you validate via the specification, right? You can say, hey, stakeholder, here's how I modeled the requirements. Do you agree with this model? Are we on the same page? Right? So you can further validate using the specification. And then management. And management accounts for changes to the requirements during the lifetime of the project. And this process is not linear, but iterative. That's why you see this spiral here, but you keep on going through these over and over and over again, especially depending on the lifecycle model and how flexible it is. But basically, you keep on doing this until the requirements are well understood. If you have a model that's flexible, then you're going to be taking on new requirements, so you have to keep on doing this, right? If the requirements are misunderstood, you got to go back to elicitation and re-ask it and reanalyze it, re-specify, etc. So it's an iterative process. Next phase is design. This is the phase where software requirements are analyzed in order to produce a description of the internal structure and organization of the system. This description will serve as the basis for the construction of the actual system. Traditionally, the software design phase consists of a series of design activities, normally consisting of the architectural design, abstract specification, interface design, component design, data structure, and then algorithm design. What you'll see is that different books and different resources will have these activities described in many different ways, right? So they'll have a prescribed way of doing this design phase. But they're all similar in that they share the same core idea, important point. And that is that we start from a high-level view of the system, which is the architectural design here. And if you see the arrow, right, we're moving towards a low-level view of the system, which is this algorithm design. All right. So high level, architectural, which is the blueprint. And then you see how we're going more low level. We got abstract, interface, so the actual API, and then the components that make those interfaces up, and the actual data structures, down to then the algorithms. So your high level down to the low level, you're working your way down. And then these activities result in a set of design products, which describe various characteristics of the system. They describe the architecture of the system, how the system is decomposed and organized into components, and the interfaces between these components, right? How they communicate. They also describe these components in a level of detail that is suitable for allowing their construction, right? So all these things that you're doing here, all this designing, right, that you're doing here has to be specified, has to be displayed. Again, whether that's pictures, diagrams, charts, words, whatever it is, you need to come down to the specification so that you can further communicate that design. And at some point it's done at the level of detail that allows for the construction, which is the next phase, the implementation phase, where you're actually constructing the system. There are four fundamental principles, four pillars that can affect the way in which software is constructed. First pillar is reduction of complexity, which aims to build software that is easier to understand and use. Then you have anticipation of diversity, which takes into account that software construction might change in various ways over time, and that software often evolves, and often in unexpected ways. Third pillar is structure for validation, aka designing for testability. So what this means is that we want to build software that is easily testable during the subsequent validation and verification activities. So the next phase is validation and verification, right? So we want to structure our code in a way that is easily testable. And the final pillar is user standards, whether that's internal or external standards. It's important that software conforms to a set of internal or external standards, and this is especially true within specific organizations and or domains. Now, internal standards might be anything like coding standards, right? Best practices you use in your organization. So usually when you start working at a software company, you're a software engineer, you have to look, or you have to learn, I should say, certain software standards. So usually you're, given some documentation, some sort of training that says, hey, at this company, we code this way, we use these naming standards, we use this indentation standards, et cetera, right? And this way, it is easy for you to read others' code and for others to read your code and be able to work faster. Keep things organized, legible, and easy to document. Now, you can also have external standards, which are standards that are imposed to you by the outside world. So let's say you're developing some kind of medical software. Then, well, we know that the medical field has sets of regulations, right? Laws and regulations, like HIPAA and privacy laws. Same thing if you're developing some kind of educational tool, such as like Bursar tools, where you have student payments and financial information, and even grades, right? Grades have privacy laws. So you have to be able to code following those standards. Next phase is verification and validation, right? And this is the phase that aims to check that the software system meets its specification and fulfills its intended purpose. And we can look at verification and validation independently. Validation answers the question, did we build the right system? Whereas verification answers, did we build the system right? Right? Subtle difference, very subtle. In validation, where we're saying, did we build the right system? We're basically answering the question, did we build the system the customer wants? Whereas in verification, where we say, did we build our system right, is, does it actually work as intended, right? So does it actually work? Does, if I input X, do I get the correct output Y? Right? So very subtle. So I create a method and it expects the input X. And for that input X, you expect the output Y, right? As verification, you want to map X to Y. That's what your unit test is doing. You call a method with a certain input, and then you're testing for a certain expected output, right? That's verification. Did we build the system right? Does it actually work? Did we eliminate the bugs? In validation, we're actually, did we build the right system, which is, did we build the system that the customer actually wants? So yeah, your method might work. It might be syntactically correct. It works. Excuse me. It might give you the right output, right? 2 + 2 = 4. You get that. But did the customer even want that? Did they want that method that does that function? Maybe not, right? So subtle difference. When you're doing verification, there are different levels of verification you can do. You got unit level testing, which is where you test that individual units work as expected. This is what you're doing for assignment 3, right? It's called JUnit. That's the software, the tool you're using, but you're basically doing unit testing. You're testing individual units. Then you have integration level testing, which is where you test the interaction between different units and make sure that the different modules talk to each other in the right way. System level testing is where you test the system as a whole. You want to make sure that all the system, all the different pieces of the system work together in the right way. And this is also the level at which you will apply validation testing and some other testing techniques such as stress testing and robustness testing and so on. Now, like I mentioned, you're doing unit testing. In real world software, when a developer develops a unit, they develop the test for it. When those unit tests pass and go green, you will then commit and push your code. And usually automatically that code is then picked up, that push new code, and it's then passed to a server that integrates your code. Basically builds all your code with the rest of the software system and test it all together. And then that succeeds, then you move on to system testing. And remember, that's where you test the whole system, and you're also doing validation testing and stress testing, right? Stress testing is like, let's mimic 1 million users, right? Let's mimic our peak use case and see if our system can handle it. If it still moves fast, if it doesn't crash due to too many server requests, etc. I'm going to talk more about this when we do the CI CD lesson, right? The DevOps lesson. DevOps, if you remember that lesson, that teaches you about CI CD. And we'll talk a little bit more about this process here. Last phase, maintenance phase. So software development efforts normally result in the delivery of a software product that satisfies the user requirements, hopefully. Normally, our software development organization will release this application to its final users. However, once the software is in operation, many things can happen. For example, environments might change. There might be new libraries. There might be new systems that our software has to operate under. There might be feature requests. So a user may find out that they want to do something differently, or maybe they want to add a functionality. And finally, one of the most common occurrences is bugs. So users will file bug reports. All right. So what you're seeing here in this deck is you have the software developer. You can think about that as the company as a whole, releasing a version of the application to the public, and then the user base starts to report back these type of changes: bugs, feature requests, and environmental changes. We will then take action that falls under these 3 types of maintenance actions. And they're self-explanatory. Corrective maintenance applies to correcting bugs. Perfective maintenance applies to perfecting the software. So including all these feature requests to make the software better and better and try to perfect it. And adaptive maintenance to adapt to environmental changes. All right. And one of the main reasons why the maintenance phase is so expensive is due to something called regression testing. Every time you modify your application, you have to do regression testing on the application, where regression testing is the activity of retesting software after it has been modified to make sure the changes you perform to the software work as expected, and that your changes did not introduce any unforeseen effect. Okay, so we see this all the time, right? Even in our small software projects at school. You're developing a small piece of, code, a class or whatever, some functionality, or, you're given a homework assignment or a small project. And what happens is you take on requirement A, right? Feature A, right? And you write the code for it and you test it. You basically, you get rid of all the syntax issues. You get rid of all the functionality issues. It's functioning, it works. You tried it with all these different inputs and it's good to go. So you move on, right? You commit it. And then you come and you take on feature B. And you do the same thing. You code it. You get rid of all the syntax issues. You get rid of all the functionality issues. So now it works. It functions. You got rid of all the bugs. You tested it with a bunch of inputs, and it's good to go. But all of a sudden, when B is good to go, and you go back and try to redo what A does, A no longer works. Right? As developers, we see this all the time, even on small projects at school. So imagine this on a larger scale. This is called a regression error. And what you're doing is you are regression testing often, because obviously we're modifying the code often. And every time we modify the code, we got to test everything that worked before to make sure it's still working. This is the reason that we create the test suites, right? So those unit test cases you're creating belong to a test suite, and then they'll have integration testing, remember this, and then system testing. All this will be automated, right? You'll grow that suite, and you'll add more and more and more test cases, more and more test scenarios, because your product grows, there's more features added, therefore you need more and more tests. And you want to automate this, right? You want to add all these tests like we're doing with JUnit, where we can just click on a button and run all our test cases, right? I know when you're in school, you run all your tests manually. You add feature A, you run a bunch of inputs manually, you add feature B, you rerun the whole program manually, and you're constantly re-executing, pressing that green play button, and playing around with different inputs to make sure all your scenarios work. You're doing this over manually. How are you going to do that if you're developing something like, Microsoft Excel, something on that level? You're going to really walk through every single feature to see if they all still work? Impossible. What you do at school will not work in the real world. So that's why you need to create those unit test cases I'm showing you in assignment 3. So that whenever you change something, well, you add more tests to that change. If you add a new feature, well, you add more test cases for that new feature. But when you press that green button, it's going to test all the test cases, even the old ones that passed already, because maybe they no longer pass. That will signify a regression error. Questions on those 5 phases? Any questions? All right, moving on. Remember the beginning, Professor Beam, the father of software engineering, said, when asked, what is a software lifecycle? He said, it's basically answering what should I do next and how long should I do it for, right? So that's what this is talking about here. Software process model. It is a prescriptive model of what should happen from the very beginning to the very end of a software development process. Main function of the lifecycle model is to determine the order of the different activities so that we know which activity should come first and which one should follow. And another important function of the software lifecycle model is to determine the transition criteria between activities. The model should describe what should we do next and how long should we continue to do it for. So basically, different software lifecycle models basically take those phases we talked about in the previous slides and determine the order, right? Which one comes first before the next one. And then they establish the transition criteria. So when am I ready to move from here to here, right? So again, what should I do next and how long should I do it for? That is the difference between each life cycle model. Quick overview of some models. First one is waterfall. Considered the grandfather of all life cycle models. Probably one of the most rigid ones, right? One of the least flexible ones. In the waterfall model, the project progresses in an orderly sequence of steps. From the initial software concept all the way down until the final phase of system testing. At the end of each phase, there will be a review to determine whether the project is ready to advance to the next phase. Pure waterfall model performs well for software products in which there is a stable product definition, the domain is well known, and the technologies involved are well understood. In these kind of domains, the waterfall model helps you find errors early. All right. So again, very rigid model. You have to finish a phase completely and pass that phase, be approved, so then move on to the next one. Right? So when I progress to a phase, to the next phase, I really don't go back anymore. I don't make changes. So that's why it's called rigid, right? Not flexible. Doesn't really allow for changes. Good thing about this is that it finds errors early. Well, since I'm perfecting a phase before moving on, I'm making sure these early phases are concrete, right? Are well done, of high quality before I move on. The con is, right, the downside is it's not flexible. If I want to make a change later on, add a requirement, modify a requirement, that's not really allowed because I already passed those phases. So very rigid, but this has its use case. Next model. This model was first described by Barry Beam, same professor from that first slide. He described this in his paper entitled A Spiral Model of Software Development and Enhancement. All right. And one of the main characteristics of that paper is that it was describing this spiral model that you see here using a diagram which has become very popular. Now, I know this slide is a little ugly, but again, this diagram is very popular. So if you just, like Google spiral model, software dev or whatever, you'll see this image everywhere. Different variations of the image, but basically all the same. Here's like the one that we're using on that slide deck. So you can find this anywhere, if you can't see it well on my slide deck. All right. And I don't want you to dig into this model. Don't worry, you can't really see these small letters. The point is that the spiral model is an incremental risk-oriented lifecycle model that has 4 main phases. All right, you got the determine objectives, identify and resolve risk, develop and test, plan the next iteration. All right, and in identify, resolve risk, the first one is determine objectives. The requirements will be gathered. When you identify, resolve risk, the risk and the alternate solutions will be identified. So this is a risk-oriented lifecycle model. So you're always worried about the risk of failure, risk of not completing the project on time, risk of being able to complete that requirement, etc. The risk and the alternate solution will be identified and a prototype will be produced. So you produce a prototype early on. Next phase is develop and test, where you produce software and test the software. And then you plan the next iteration. So the output of the project so far is evaluated, and the next iteration is planned. And the software project will go through these 4 phases in an iterative way, right? That's that spiral. So basically what the spiral process prescribes is a way of developing software by going through these phases in an iterative way in which we learn more and more of the software. We identify more and more of the requirements and account for more and more of the risk, because this is risk oriented, while working towards our final solution, our final release, which you see here. When the arrow ends, we release. So there's several advantages. There's a risk reduction advantage. So there's extensive risk analysis done to reduce the chances of the project failing. So there's a great advantage in doing this because we reduce the reduction of failure. Another pro is functionality can be added along the way. Oops, I meant to square this. I wonder how to. I guess I can't undo that, or I don't know how to, but I can erase. Cool. All right, so yeah, I'm up to here. I did risk reduction, and here's functionality can be added along the way. So functionality can be added at a later phase because of the iterative nature of the process. So we kind of do in the beginning a prototype. So you know, I hope you know what a prototype is. It's kind of like a sample of the project, an example of it, but not completely baked. And by that we get early feedback. And when we get early feedback, we can then correct our course. So if we're on the wrong path, we can correct our course. So that's part of the software is produced early, which allows us to get early feedback and then allow us to add not only correct functionality or correct requirements we misunderstood by getting that early feedback from those prototypes, but also add functionality if they feel things are missing or features that can be at advantage. The cons of the spiral model is that you need specific expertise, right? So risk analysis requires a highly specific expertise. And since the whole success of the process is highly dependent on risk analysis, the risk analysis has to be done right? So highly dependent on it. This is way more complex than other models. You can even see it just in this diagram itself. And therefore, it is costly to implement, right? All that risk expertise needed, that domain expert, that risk analysis expert, all that makes this complex and expensive. Next model I want to talk about is evolutionary prototyping. So it works in 4 main phases. You have the initial concept, then you design and implement a prototype based on that initial concept, and then you refine the prototype until it is acceptable. And then you complete and release the prototype. So when developing a system using the evolutionary prototyping, the system is continually refined and rebuilt. It is an ideal process when not all the requirements are well understood, which is a very common situation. Developers start by developing the parts of the system that they understand, and instead of developing a whole system, including parts that maybe they don't have a clear understanding of, what they do is they prototype that partial system and then show it to the customer, to the stakeholders, and then use that feedback to drive the next iteration, in which either changes are made to the current features or new features are added. So either the current prototype is improved or the prototype is extended, right? Improved, which is fixing issues, and then extended, which is adding features. So when the stakeholders finally agree that the prototype is good enough, the developers will complete the remaining work on the system and release the prototype as the final product. So this is, you might say, hey, this is like Spiral. It's a little bit different in that there's no risk analysis, right? We don't have that risk complexity added to it. And we're mostly worried about this prototype and getting it right. The main advantages is, again, immediate feedback. So as soon as you produce a prototype and you show it to the customer, you're getting some feedback on if you're heading in the right direction. The risk of implementing the wrong system is minimized, right? Because it helps requirements understanding. The main disadvantage is it's difficult to plan. So it's hard to plan in advance how long the development is going to take because we don't know how many iterations will be needed. We can always accept new requirements. We can also, we can extend it, we can adapt. So we're always in this refining phase until accepted. So you can't really plan how long it's going to take, how much money is going to cost, how many development hours you need. All that becomes very difficult to plan, which can be important. Another con is that it can easily become an excuse to do kind of a code and fix type approach, in which we hack something together, fix the main issues, and then when the customer gives us feedback, we'll fix it at that point. So we'll continue this way until the final product. So the final product will be something that's kind of working, but it won't be of high quality because we're just hacking this together, waiting for the feedback to fix it, right? We're not coming with our best foot forward straight from the beginning. There are many types of prototyping. Evolution prototyping is just one of them. Throwaway prototyping, for example, is another kind of prototyping in which the prototype is just used to gather requirements, but then it's thrown away at the end of the requirements gathering phase instead of being evolved as it happens here in evolutionary prototyping. Rational unified process. So a very popular process model based on UML. UML stands for Unified Modeling Language. And Unified Modeling Language is a very good language to model requirements that are going to be used to implement object-oriented programs like Java, C++, C#, etc. Right? So for object-oriented paradigms, UML is a good modeling language to model those kinds of systems. And RUP is heavily based on UML. And I know this chart might look a little confusing, but basically what you see here are the 4 phases that RUP consists of, right? So RUP consists of many iterations, and each of the iterations performs these 4 phases. And then these 4 phases themselves have these inner or sub iterations, right? And you can see how these phases map to our generic phases on the left here. Requirements, design, implementation, testing, deployment, right? So they're a little bit different, but the same thing, right? Requirements engineering, design, implementing, verification, validation, maintenance. There's an extra one here called business modeling, which is kind of where you make your case to the business, right? To the higher ups. Hey, this is the what we're trying to create, and this is the business justification for it, right? So you're looking at it from that perspective. And what you're seeing here in the chart is kind of how each of these phases map to these phases. So how much of this you're doing in each of these iterative phases. For example, you see here in the inception phase is where you start the requirements gathering. Well, after you do a lot of the business modeling, which you do a lot of that in the beginning, and then that kind of goes off. But requirement starts in the inception phase, and then it goes, at its peak during all of elaboration, a little bit during construction, and then kind of goes down. The design, obviously, after you gather the requirements and during gathering the requirements, depending on how you're iterating, you have a lot of that going on, even towards construction, depending on how you're iterating, right? You're building and fixing, especially if your construction involves prototyping like Rational Unified Process does. And then obviously implementation is mostly during the construction phase. And you have testing all around. And you can see the peaks are usually at the end of these sub iterations, right? Or in between them where the peaks are. And then deployment starts very low during elaboration, right? Maybe prototyping, and then actual beta, alpha, beta, and then finally you're releasing that final product during that transition phase. I'm not gonna get any deeper into this. We have a lesson dedicated to this process, so we'll get way deeper into understanding this model, this graph here. I just wanted to give you a quick overview. Finally, Agile. Somebody asked me, all those parts, we the team all agree on something on the design. I'm not sure what you're asking. Are you asking about all these lifecycle models do you choose? Actually, for your team project, you're going to be giving like a slimmed down version of the Rational Unified Process. So that's why we do this in a lesson, and then you use that for your team project. Again, a slimmed down version. I'm not sure if that's your question, a little vague. All right, Agile. So here, this slide talks about TDD, test-driven development. This is not a good slide to describe Agile. If you want to understand Agile more, go to the internet and actually type like Agile. And even if you go to this Wikipedia page, this is not a bad place to kind of get a good summary of what Agile is. So I'm going to paste this link in the chat. And what I want you to see here on this right-hand menu, right, this menu bar, is some of the stuff we've been discussing so far, right? So I want to make sure that you see this. This is a way to easily browse different parts of software development. And we're talking about the same thing we're talking about in this class, software engineering, right? Software development life cycles. So first you see here, core activities. And these are the same activities we discussed in our slide. So we go back to this traditional software phases, requirements, design, implementation, maintenance, and so on. Look, requirements, design, engineering, construction, testing, debugging, which is part of testing, deployment, which is part of that whole phase of testing and deploying, and then maintenance, which is this maintenance phase, right? So they're naming, they have some extra ones, some of them we merge together, etc. But it's basically the same set of core activities. And then we look at paradigms and model. Look, we got waterfall here. We just discussed that. We got spiral. We just discussed that. Prototyping, right? Remember, there's many types of prototyping. Here we go to different types of prototyping. Look, they're there. Throwaway is one of them. I'll just look at the contents menu. Here, they got dynamic systems, operational prototyping, evolutionary prototyping. Here, types of prototyping. Perfect. Yeah. Types of prototyping. Throwaway prototyping. I discussed that really quick. Evolutionary prototyping. That's exactly what this was, right? We spoke about here, evolutionary prototyping. Incremental prototyping, extreme prototyping, right? So there's different styles of prototyping, and they're there in this menu. Then you have methodologies and framework, right? A lot of these seem to fall under the agile paradigm. So here's DevOps. We're going to discuss that, right? We have a lesson dedicated to that. We have extreme programming, XP. We're going to discuss that in our agile lesson. We have Scrum. We're going to discuss that in our agile lesson. And there's many more. And there is practices that make up these frameworks. And you see here, TDD, test-driven development is one of them, right? And then tools. Well, look, compiler, debugger, GUI designer, IDEs, build automation. We'll talk about build automation in DevOps lecture, release automation in the DevOps lecture, infrastructure as code in the DevOps lesson. We're going to do a lot of testing. You started unit testing in your assignment number 3, and we're going to discuss testing even further. Right, so IDE is there, right? They should talk about repository control should probably be in here. Right? So you have a lot of things, IEEE standards, etc. So this is a good outline of what we're doing, and you can see that what we're discussing is part of the discipline. All right, you really want to understand Agile, you want to come here and kind of read this description. But basically, Agile is a group of software development processes that are based on highly iterative and incremental development. All right, so highly iterative and incremental. Incremental as in, I don't try to get all my requirements in one shot and then develop the whole system. What I do is I try to understand a piece of it and implement that piece at a time, and then come back and do it again and do it again. So kind of like that, like prototyping, but you're not really coming up with prototypes. You're actually releasing working pieces of the software to the public. And we'll see that when we get to Agile. And it's a lightweight of doing that. We're not too worried about a lot of documenting because, well, if our software system is constantly changing, constantly evolving, then why do we want to keep on documenting to just change that document? So we do that in a different way. We do document, but it's done in a more lean way, as they call it. All right. So Agile is way too big to like describe every aspect of it. You can look at like Agile versus Waterfall, etc. But here are the frameworks. And again, we're going to do extreme programming. We're going to discuss a little bit about Kanban, Scrum. I would say Scrum is probably one of the more popular ones used today in our field. And when we talk about practices, we'll talk about a lot of these practices. We're going to talk about CI/CD, daily stand-ups, daily scrums. We'll do pair programming. We'll do Scrum events, test-driven development, user stories, etc. Okay, there's just a lot to it. So, all right. Any questions on Agile? Again, this is just a brief overview. All right. Here, TDD specifically consists of a practice called test-driven development. It's part of extreme programming. Is one of the methodologies, the Agile methodologies that uses them. And basically, this is where you write tests before you code. So step one is to write a test that fails, and it fails because there is no code to make it pass. Step two, make only enough code to make the previously failing tests pass. And then step three, refactor, so improve code quality. And we'll discuss this further in the future. Now, the specific process model that we choose has as much influence over a project success as any other major planning decision that we make. So it is very important that we pick the appropriate model for our dev process. Picking an appropriate model can ensure the success of a project, whereas if we choose the wrong model, that can be problematic and ultimately lead to a project failure. So how do we choose the right model for our project? To be able to do so, we have to take into consideration many factors. In particular, level of understanding of the requirements, right? Do we understand all of them? Are we going to be able to collect all the requirements in advance? Or is collecting requirements going to be hard? And therefore, we might want to follow a process that is more flexible, right? We can collect everything in advance. We can go really rigid, like waterfall. If we can't, if we don't know all the requirements up front, then we need to go agile, right? We need to be more flexible, something that allows us to keep on adding requirements as we move forward. Expect the lifetime of a project. This is a quick project that we're putting together for a specific purpose. Or is it something that's going to last a number of years and we're going to have to support it all those years? Risk. What is the level of risk involved? Do we know the domain very well? Do we know the technologies involved? If we do, we can go with a more traditional process. Otherwise, we might want to be more flexible. Know the schedule constraints. How much time, how many resources do we have for this project? What is the expected interaction with management and the customers? There are many processes, right? Many lifecycle processes that rely on the fact that there is continuous interaction with customers. Conversely, there are processes that do not require the presence of the customer at all, except for maybe in the initial phase, right? So if we have an accessible client, then we want to follow one of those processes. If we have a more demanding client, one that wants to be really involved, then we want to pick the appropriate process model. So obviously, if we're a company that, like a third-party company or whatever, that creates software for other companies, we get hired, right? And that customer is probably going to be highly involved. They're spending money on us. They want to be there, have overview, et cetera. They're going to be able to answer our questions. So we can pick the model that supports that. Whereas maybe if you're doing a mobile application like a social media platform or something, you don't really have customers buying your software directly. You just hope they use it. So you're not really going to have that kind of interaction. You're going to, you can do research, you can do surveys, but you're not going to have an interaction. So you want to use a different kind of model. And then you have expertise, right? So what is the level of expertise of the people involved? Do we have the people that know the text? Do we have people that know the specific kind of process, right? The process we're going to use, the process model. Some processes require specific expertise, such as like Spiral, right? Spiral requires that we know we can do risk analysis, and we have those domain experts to do that. So you're going to have to know if you have the availability to apply those models. So we need to take into account all these aspects and maybe some more in order to be able to make the right decision and pick the right software process model for our project. And again, we can use hybrid of them. We can use a mixture of them. It's not one size fits all. Our project can be huge, and we might break it down into sub-projects, sub-components that can then each use their appropriate lifecycle model. There's also lifecycle documents. So documenting the activities carried out during the different phases of the software lifecycle is a very important task. The documents we produce are used for different purposes, such as communicating details of the software system to different stakeholders, ensuring the correct implementation of the system, facilitating maintenance, and so on. So for example, right, where it says facilitating maintenance. So let's say I have requirement 1. This is requirement, whatever, 1.3, I don't know. So that's requirement 1.3. When I go to the design phase, if I annotate my design with the requirement it's fulfilling, then it's really easy to map that. Then that design becomes the implementation, right? So if I comment or somewhere in my API say, hey, this part of the code, this part of the implementation is for requirement 1.3. Well, then it becomes very easy if I need to make a change, right, to the requirement. I know exactly where the design is affected. Therefore, I know exactly where the code is affected. If I have a bug when I'm in my testing phase, if I add 1.3 to the test cases that map to requirement 1.3, well, if I have a bug, I know exactly where my test cases need to be improved. Or if I modify something in the code in the implementation, what test cases need to be modified to handle the new changes, right? All this is part of facilitating maintenance, keeping track of things, and being able to communicate the details of the software system. IEEE has a standard set of documents provided for this purpose, for documenting the lifecycle phases. Very heavyweight. So for our purposes, for our project, we're going to use a lightweight version of these documents. All right, that's the end of that. Quick question, you can type the answer in Teams. Which of the following models is most suitable to develop a software control system? Again, this is a software control system for something critical, maybe like an airplane software control system. What kind of model is suitable for that type of software system? All right, so I got a couple of people that are awake and paying attention. Definitely pure waterfall. So remember, in pure waterfall, you have to get all your requirements set in stone before you can move forward. They all have to be approved. This is obviously a good use case for this kind of model because no, I cannot accept changes in the middle of development. No, I can't just add requirements. That's a high risk, highly dangerous, and can lead to bugs, right? That then cause catastrophic failures, right? Lives are at stake. Next, which model is the most suitable if you expect miscourse correction? So this is where I don't know all the requirements up front. Maybe my stakeholders are unsure, so they're gonna, change the requirements in the future or give me more requirements. What's a good one for that. Cool. I'm getting a lot of evolutionary prototyping. Yes, that's a perfect one for that. You can even get away with spiral, right? So if you remember in the spiral, you initially give a prototype, and then you take feedback and further iterate based on that initial prototype. So yeah, it's not as flexible as evolutionary prototyping, but it will work with mid-course corrections. That's the point of the spiral model as well. All right. So we have what? Okay, we have 10 minutes left. Cool. So let's go really quick through what I said I would wrap up the lesson with. It's just a quick list of classic mistakes made in software development that can lead to failures. We want to know about them so that we avoid them. So the first one you see here is heroics. And in heroics, you have too much emphasis on can-do attitude. The idea that one person can do everything, right? So you have that star coder that you think can get everything done by themselves. This encourages extreme risk-taking and discourages cooperation. It might force people to not report schedule slips. It might force people to take on too much responsibility. So normally the final result is failure. If you have a larger project, you need to have teams, and you need to understand how to break up the work between the team members and have them cooperate. Next is work environment. So there's strong evidence that the work environment can play a big role in productivity. Evidence that productivity increases when the workplace is nice, quiet, warm, and welcoming. That's why you have these big companies investing a lot, right, into their real estate. They have gyms, they have game rooms, they have some of them have daycare, they have dry cleaning services. They'll cook for you, right? So like Google gives you breakfast, lunch, dinner, all these things so that you're comfortable, you're stress-free with everything outside of work, everything is handled for you, and therefore you produce better quality code. I mean, it also probably makes you work 12 hours a day because you're comfortable there. And, that's all for their benefit. Poor people management. So lack of leadership or leadership that is exercised using the wrong means in the wrong way, which can lead to very unhappy personnel and low productivity, or even people leaving the team. So a lot of turnover. Adding people to a project that is behind schedule never works. So you never want to do that if you're managing people. If a project is behind, you want to try to see what's causing it to fall behind, but not just add people to it. When you add people to it, they have to be caught up. There's a big learning curve, so usually the project is delayed even further. Classic mistakes in the process. So there are scheduling issues due to the fact of being unable to come up with a realistic schedule. So having an overly optimistic schedule because we underestimate the effort, that's a big one. So usually we overestimate the ability of people or the ability of just being able to develop a software, system or a component of that software system. It's a lot of work. It's always more than you think it is, especially with everything surrounding it, like planning, designing, testing, debugging, etc. Another mistake is planning issues. So such as insufficient planning or abandoning planning schedules due to pressure. So what happens is you'll come with a plan, you'll say, hey, we're going to do it this way. And all of a sudden you got a lot of pressure from up above that, hey, can you get this done faster, et cetera. And then you just forego the plan and just start doing things ad hoc. That leads to failure. All right. Classic mistakes in product. First one is gold plating of requirements. So basically, it is very common for products to have more requirements than they actually need. So for example, marketing might want to add more features than the ones that are actually needed by the users. Having more requirements lengthens the project schedule in a totally unnecessary way. Feature creep is another similar one, where it consists of adding more and more features to the product that were not initially planned. All right, so it says on average, project experiences about 25% growth in the number of features. So this is different than the first one. The first one is the requirements, right? Gathering or adding more requirements than you gathered or needed. Feature creep is just as I'm developing, I'm adding more and more features. I'm, coding for more scenarios that are unneeded, that are not needed. All right. The last one you see here is R does not equal D. So research does not equal to development. So if you're working on a project that strains the limit of computer science, for example, you need to develop a new algorithm or solve a problem that hasn't been solved before, something like a large scale problem, that is not something you want to do during development. That is something you want to do in a research phase. You want to have the research team doing that. That puts a project behind, and that leads to failure, right? You don't even know that if you're going to succeed, if what you're researching is possible, has a possible solution. When you develop, you know exactly what you need to do. You know what you're going to use, which type of data structures and algorithm. If you're during development, now you have to solve a brand new problem, that's considered research. So you need to separate the two. Classic mistake in technology. You got the silver bullet syndrome. So this refers to a situation where there's too much reliance on the advertised benefits of some previously unused technology. So for example, new tech, or expecting technology alone to solve all our software development issues. So don't rely on tech too much, or especially on unknown technology, or technology that promises that it's going to do all these things, and when you actually go use it to develop your software system, it doesn't do half of what it says it promises. Next is switching tools or adding tools in the middle of the project, a big no-no. It's okay to sometimes upgrade a tool, right? Upgrading can be okay, but don't introduce new tools because they can have a steep learning curve which push you behind schedule. And last but not least, lack of automated version control system. We know this is a big one. We are teaching you Git and GitHub for this purpose. You cannot be at a big company without version control, where you know exactly who's adding what lines of code down to the characters and white spaces. If a bug is introduced, I can rewind. If code goes missing, I can recover, etc. This is a must. And that's the end of that. Any questions at all on this lesson? Yeah, somebody said also make you work more. That's probably to the part where making your environment comfortable. Yes, I agree. It's a psychological move that benefits them, right? So make you work with higher quality because you're comfortable. If you're comfortable and you're not thinking about all the outside stresses, you're being fed, you're being given fruits and snacks, so you're full. If you're, they have daycare services, so your kid needs to be taken care of. So they're taking care of all these things and making you more comfortable in order so that you have produce higher quality because you're stress-free. But it also leads to you working more. That's 100% true. I mean, when you're comfortable, when you have games and you have food, you stay there, you work more hours. By the time you realize it, you work 10, 12 hours. And also minimizes turnover, right? Which people quitting. If you have a good developer, you don't want them to leave your company. All right. It says, when can we see the assignment to be graded? So when will the assignment be graded? I will probably by the end of this week, I'll have assignment 1 and 2 graded. Obviously, I can't grade 3 yet because it's not due yet. Is the assignment due date supposed to be Sunday and not Monday? I'm not sure what you mean. I don't remember the assignment due date, but whenever it is, that's when it is. I made it on, are you asking me if, I think I made it on Sunday. Are you asking me if it should be Monday? Are you going to make me log into Blackboard and check the due date? Making me work. Let me go into Blackboard. This is section 34. And I hate Blackboard. You gotta do so many things just to see one thing. Assignments 2. Oh no, wait. Assignment 3, right? Assignments 3. So Sunday. That's enough time. Were you guys crying about the time? I didn't want you guys working on my assignment during class. So that's why I made it Sunday. It gives you more than enough time. If you guys feel a crunch at the end, let me know. I can give you like an extra day, but I don't think it's necessary. I mean, you should be able to do it in one day. Somebody said here, ex Google tech lead and ex Facebook. Are you an ex Google tech lead, or are you referring to somebody else? The non. Okay. I'm about to say, man, you don't have to. Shouldn't be in this class if you are. Okay. So he's a YouTuber that must be explaining how it makes you never want to leave. But obviously, if you want to create your own company or startup, or just go off on your own, you're gonna have to leave those kind of places. They require a lot of your time. But I'm not sure exactly what that YouTuber is referring to, but I imagine it's something like that. So any questions? Assignment 3. Again, I'll try to grade everything by, I don't have to teach tomorrow. So hopefully tomorrow I can get it all done. Latest by this weekend, you should have your grades for 1 and 2. And then when you hand in 3, I should be able to start grading those. All right, time is up. It's 9:16. I don't want to keep you over like I usually do. So I will see you next week.